The Milky Way galaxy is home to billions of stars, many of which are larger, brighter and hotter than the Sun. Stars exist in a wealth of different varieties which drive their unrivaled sizes, with the scale ranging from stars the size of Jupiter to stars larger than Jupiter's orbit around the Sun. You've likely all seen pictures of the latter, various giant stars which completely dwarf the Sun, rendering it as nothing more than a grain of sand next to a beast of the cosmos. But how do we arrive at these conclusions? How do we measure stars to identify these mind-blowing sizes? And above all, which of them is the biggest? At its heart, a star is a colossal luminous sphere composed almost entirely of hydrogen and helium. But this isn't gas as we know it. The immense heat and pressure strip electrons from their atoms, creating a fourth state of matter, plasma. This forms an ultra-energetic soup of free-roaming atomic nuclei within a turbulent sea of electrons. Deep within the star's core, conditions are extreme. Temperatures soar past 15 million degrees Celsius, and the pressure is billions of times greater than on Earth. Under this relentless gravitational crush, hydrogen nuclei, which normally repel each other, are forced so close together that the strong nuclear force takes over, fusing them into helium in a process called nuclear fusion. Our own Sun is a perfect example. Every second it fuses about 600 million tons of hydrogen into helium. However, the resulting helium weighs slightly less. That missing mass is converted directly into a phenomenal amount of energy, according to Einstein's famous equation, E=mc2. This is the energy that powers the star, radiating out as light and heat. This constant energy release creates a powerful outward radiation pressure, pushing against the relentless inward pull of gravity. The two forces become locked in a delicate balancing act known as hydrostatic equilibrium. This stability is what allows a star to shine steadily for billions of years, existing as a perfectly contained, self-sustaining nuclear explosion, a beacon in the cosmic darkness. But how does this engine ignite? The journey begins in vast cold clouds of gas and dust called nebulae, or stellar nurseries. Spanning light years, these clouds are mostly hydrogen and helium. Often, a trigger, like a shockwave from a nearby supernova, is needed to disrupt the cloud, causing dense pockets of gas to begin collapsing under their own gravity. As the clump of gas contracts, it spins faster and heats up, forming a glowing embryonic star known as a protostar. For thousands of years it gathers more mass from the surrounding cloud, its core growing ever hotter and denser. Finally, when the core temperature and pressure reach the critical point, the ultimate alchemy occurs. Hydrogen nuclei begin to fuse, igniting the star's plasma furnace in a brilliant flash, and a new star is born. After a star ignites, it enters a long, stable period known as the main sequence. Here, a delicate balance is struck. The inward crush of gravity is matched by the outward pressure from nuclear fusion in the core. This state, called hydrostatic equilibrium, is why stars don't change much in size for the vast majority of their lives, which can last for billions of years. But this equilibrium is temporary. Once the core's hydrogen fuel is exhausted, gravity gains the upper hand, compressing the core and raising its temperature. This ignites hydrogen fusion in a shell around the core, generating even more energy. This intense outward pressure forces the star's outer layers to expand enormously, transforming it into a giant. Our own Sun will follow this path in about 5 billion years. As it exhausts its core hydrogen, it will swell into a red giant, expanding to over 250 times its current diameter. Its luminous but cooler surface will consume Mercury and Venus. Earth's fate is uncertain. It may be vaporized by the Sun's expanding atmosphere or left a charred barren cinder. But how do we measure the size of these distant giants? The key is the Stefan-Boltzmann law, which links a star's radius to two properties: its total energy output, or luminosity, and its surface temperature. To find the radius, we must first find these values. For nearby stars, distance can be found using parallax, the apparent shift in position as viewed from different points in Earth's orbit. Knowing the distance helps calculate its true luminosity. For temperature, we analyze the star's light. Its spectrum reveals its temperature, while unique absorption lines act like a fingerprint, helping us classify the star and refine our luminosity estimate. For a time, the undisputed heavyweight champion of the cosmos was thought to be Vy Canis Majoris. Located about 3,900 light-years away, this star is a red hypergiant, a rare and incredibly luminous star that has evolved past its main sequence phase. Its designation as oxygen-rich hints at its advanced age, while its pulsating variable nature means its outer layers are unstable, causing it to rhythmically expand and contract. This instability is a hallmark of a star nearing the end of its spectacular life. Today its radius has been more accurately measured to be around 1,420 solar radii. At this size it would be large enough to engulf the orbit of Jupiter, stretching some 750 million kilometers from its center. Canis Majoris is in the final stages of its life, and as it fuses heavy elements like oxygen in its core, the immense energy produced pushes its outer layers away. It's shedding mass at an incredible rate, creating the vast complex nebula that surrounds it. Within a few 100,000 years, it will likely exhaust its fuel and explode in a cataclysmic hypernova, potentially leaving behind a black hole. Of the few stars that were believed to rank above Canis Majoris, Ui Scuti is probably the most well-known, spending much of the last decade as the largest known star. Measuring these distant giants is a huge challenge, as they are often shrouded in interstellar dust. In 2013, Ui Scuti's distance was estimated to be around 9 or 10,000 light-years away from the Earth, yielding a mind-blowing size of around 1,700 solar radii. However, in 2018, data from the ESA's Gaia spacecraft provided a more accurate measurement. Gaia uses stellar parallax, the tiny apparent shift in a star's position as Earth orbits the Sun, to precisely map the galaxy. This new data placed Ui Scuti much closer, at around 5,100 light-years. Since the star was closer than we thought, it must be intrinsically smaller to have the same apparent brightness. Ui Scuti was the king of stars for many years, but after the Gaia data release cast doubt over its true size, the throne was once again opened for a new stellar champion. Enter the latest and new largest known star, Stephenson 2, 18. This red supergiant resides in the open cluster Stephenson 2, a remarkable stellar nursery packed with other massive stars. Because of its immense distance, we can't measure its diameter directly. Instead, astronomers calculate its size based on its temperature and luminosity. By applying Stephenson 2, 18's observed properties to the luminosity formula, they correspond to a staggering radius of 2,149 solar radii, making Stephenson 2, 18 by far the largest star discovered yet. This corresponds to a volume of almost 10 billion times that of our Sun, and it's hard to appreciate just how large that truly is. If it replaced our Sun, its surface would extend far beyond the orbit of Saturn, a truly mind-boggling scale. Over the years we have continually found larger and larger stars, and so it's reasonable to assume that something else will come along and knock Stephenson 2, 18 off the top of the list before long. These giants push the theoretical maximum size for a star, known as the Hayashi limit, beyond which a star cannot remain in equilibrium. But these stars are more than just cosmic curiosities, they are the universe's great alchemists. Through their violent deaths and supernova explosions, they forge and distribute the heavy elements, the carbon, oxygen, and iron, that are essential for the formation of new stars, planets, and ultimately life itself. But make no mistake, it will take something truly remarkable to knock this monster off its pedestal as king of the cosmos.